Hey everyone, welcome back to another video from my channel. In our last video, we discussed about forces and friction as well as resolving forces along an inclined plane. Today, we will be discussing about one-dimensional momentum and impulses. You can calculate the momentum of a particle and the impulse of a force. The momentum of a body of mass m which is moving with velocity v is mv. Therefore, we have the formula P is equals to mv. If m is in kg and v is in meter per second, then the units of momentum will be kg meter per second. And however, since kg meter per second is kg meter per second square multiplied with s, and kg meter per second square are the units of force, which is F is equals to ma, as we discussed previously, you can also measure momentum in Newton seconds. In our first example, we have to find the magnitude of momentum of a cricket ball of mass 400 grams moving at 18 meter per second. So for number A, momentum is equals to mass into velocity. Therefore, magnitude of momentum is equals to 400 by 1000 to convert the mass into kilograms and multiply it with 18, which is the velocity. Therefore, the answer is 7.2 Newton seconds. For number B, momentum is equals to mass into velocity again, which has a mass of 5 tons and a velocity of 0.3 meter per second. Therefore, we have to convert these tons into kgs, and as we know, 1 ton is equals to 1000 kg. Therefore, the answer is 5 into 1000 multiplied with 0.3, and the answer is 1500 kg meter per second. If a constant force F acts for a time t, then we define the impulse of the force to be F multiplied with t. If F is in Newton and t is in seconds, then the units of impulse will also be Newton seconds. Example of an impulse include a bat hitting a ball, a snooker ball hitting another ball, or a jerk in a string when it suddenly goes tight. In all these cases, the time for which the force acts is very small, but the force is quite large. This means that the product of the two, which gives the impulse, is of reasonable size. However, there is no theoretical limit on the size of t. Suppose a body of mass m is moving with an initial speed u and is then acted upon by a force F for time t. This results in its final speed being v. Its acceleration is given by a is equals to v minus u divided by t, and substituting F is equals to ma, F is equals to m multiplied with v minus u whole divided by t, and so we get Ft is equals to m whole multiplied with v minus u, and this is mv minus mu. So I is equals to mv minus mu, which is final momentum minus initial momentum, or the change in momentum. This is called the impulse momentum principle. In our previous videos, we have discussed about Newton's second law, where we know that F is proportional to acceleration, or the unbalanced force, or the resultant force is directly proportional to the acceleration. Therefore, F is equals to ma, where m is the mass, and we know a is equals to v minus u whole divided by t. Therefore, F is equals to m multiplied with v minus u whole divided by t, and we get impulse is equals to change in momentum. So now let's move on to some exercises. For 6a, number 2, a ball of mass 0.3 kg moving along a horizontal surface hits a fixed vertical wall at right angles with speed 3.5 meter per second. The ball rebounds at right angles to the wall. Given that the magnitude of the impulse exerted on the ball by the wall is 1.8 Newton seconds, find the speed of the ball just after it rebounds. So first, let's draw the scenario. If this is the wall and if this is the ball, it was initially traveling at a speed of 3.5 meter per second and its mass is 0.3 kgs, and after rebounding it had a final velocity v and also an impulse of 1.8 Newton seconds. So similarly, the wall will also receive an impulse of 1.8 Newton seconds, and so resolving to the left, assuming the left direction is positive, therefore we can use the formula I is equals to change in momentum, which is delta p, or mv minus mu, or m whole multiplied with v minus u. Therefore, as we know, I is 1.8 Newton seconds, and delta P, which is equals to m whole multiplied by v minus u. Mass is 0.3 kgs, velocity is unknown, which is the final velocity v, and initial velocity was 3.5. Now, if you notice, 3.5 is to the right. Therefore, because we assume that the left side is positive, therefore the right side will be negative. And so this should be minus 3.5. So simplifying, we can get 1.8 divided by 0.3 is equals to v plus 3.5, and therefore final velocity is equals to 1.8 divided by 0.3 minus 3.5, and the answer is 2.5 meter per second. And this is our answer. For number 4, a ball of mass 0.2 kg moving along a horizontal surface hits a fixed vertical wall at right angles. The ball rebounds at right angles to the wall with speed 3.5 meter per second. Given that the magnitude of the impulse exerted on the ball by the wall is 2 Newton seconds, find the speed of the ball just before it hits the wall. So similarly, just like before, the ball has an initial velocity of u, which is unknown, and it hits the wall, and after rebounding, it has a final velocity of 3.5 meter per second with an impulse of 2 Newton seconds. And so the wall should also receive an impulse of 2 Newton seconds according to Newton's third law, and therefore resolving to the left, assuming that the left direction is positive, we can say that I equals to delta P, which is mv minus mu. So applying the formula, we can say that impulse is 2 Newton seconds, mass is 0.2 kgs, velocity, or the final velocity is 3.5 minus u, because as I've said before, we're considering that the left side is positive, therefore u being in the right side is negative. So further simplifying, 2 divided by 0.2 is equals to 3.5 plus u. Therefore, u is equals to 2 divided by 0.2 minus 3.5. And the answer is 6.5 meter per second. For number 5, a ball of mass 0.2 kg is dropped from a height of 2.5 meters above a horizontal ground. After hitting the ground, it bounces to a height of 1.8 meters above the ground. Find the magnitude of the impulse received by the ball from the ground. So drawing the scenario again, if this is the horizontal surface, for number 5, it is initially dropped from a height of 2.5 meters. And as the ball drops, it will have a final velocity v. So we know from this position, initial velocity was u, which is 0. Displacement is 2.5 meters. We know that it is under free fall, therefore a is equals to g, and so we need to find final velocity v. We know the equation v square is equals to u square plus 2as. Therefore, v is equals to root over 0 squared plus 2 into g into s, which is 2.5. And as we know that the value of g is 9.8 as we used previously. Therefore, the final velocity is 7 meter per second. Now, after having contact with the surface, you can say that the ball will rebound to a height of 1.8 meters. And now we have to find out the initial velocity u just as soon as the ball started to rebound. So this will be 7, and from this point we can consider this to be another motion with initial velocity being unknown. Final velocity is 0 at the max height as we discussed in our first video. Displacement is 1.8, and because we have considered the upward to be positive, therefore the downward position should be negative. So acceleration must be minus g. So similarly again we can use the equation v square is equals to u square plus 2as. Therefore, making u the subject, we have root over v squared minus 2as, and substituting the values we have 0 squared minus 2 into acceleration, which is minus g, multiplied with displacement, which is 1.8, and so the answer is 21 root 2 by 5 meters per second. And now we can calculate the impulse, which is I is equals to mv minus mu, which is in modulus because we have to simply find the magnitude and not the direction. So substituting, we get modulus of 0.2, that is the mass, whole multiplied with final velocity, which is 21 root 2 by 5 minus 7, because if you consider the dropping motion, if this is the ball and it travels initially with a velocity of 7, then it rebounds with a velocity of 21 root 2 by 5 meter per second. So therefore this should be u and this should be v, and if we consider this to be positive, therefore this should be negative. Therefore we have minus 7, and so the final answer is 2.59 Newton seconds or kg meters per second, and this is our answer. So now let's move on to one of the most important concepts in momentum, which is the conservation of momentum. You can solve problems involving collisions using the principle of conservation of momentum by using Newton's third law. When the two bodies collide, each one exerts an equal and opposite force on the other. They are in contact for the same time, so they each exert an impulse on the other of equal magnitude but in opposite direction. By the impulse momentum principle, the changes in momentum of each body are equal but opposite in direction. Thus, these changes in momentum cancel each other out, and the momentum of the whole system is unchanged. This is called the principle of conservation of momentum. So, total momentum before impact is equal to total momentum after impact. You can write this in symbols for two masses m1 and m2 with speeds u1 and u2 respectively before the collision, and speeds v1 and v2 respectively after the collision. So we have the equation m1u1 plus m2u2 is equals to m1v1 plus m2v2. When solving problems involving collision, always draw a diagram showing the speeds before and after the collision with arrows. If appropriate, include the impulses on your diagram with arrows. Choose a positive direction and apply the impulse momentum principle and or the principle of conservation of momentum. So now let's do some practice question from past exam papers. For number 1, we have a question from Jan 2020 of question number 1. Two particles P and Q of mass m1 and m2 respectively are moving on a smooth horizontal plane. The particles are moving towards each other in opposite direction along the same straight line when they collide directly. Immediately before the collision, both particles are moving with speed u. The direction of motion of each particle is reversed by the collision. immediately after the collision, the speed of q is 1/3 of u. Find in terms of m2 and u the magnitude of the impulse exerted by p on q in the collision. So for A, we can first draw the situation, which is like this. If this is m1 and this is p, so it will travel with a velocity of u, and similarly q would also have a mass of m2 moving in an opposite direction with a velocity of u again as given here. They're moving towards each other but in opposite direction, and they have speeds of u. And this is the initial conditions, and after collisions we can say that the particles will look something like this, where p will have an impulse here and q will have an equal but opposite impulse there. So this is m1 and this is m2 with a velocity v1 and v2. Now as we know, immediately after the collision the speed of q is 1/3 of u, so we know that this velocity should be 1/3 of u, and the direction will be reversed as mentioned in the question. So we can apply I is equals to delta p, or change in momentum is equals to mv minus mu, which is the formula. And so we can apply the formula for q, and we have m2 as the mass, final velocity is 1/3 u, and we are resolving to the right. So as we know, if 1/3 u is in this direction, u, the initial velocity of q, is in the opposite direction, so this should be negative, so we have minus u, and so m2 1/3 u plus u, and so our impulse is 4/3 of m2 u Newton seconds. For number B, we have to find in terms of m1, m2 and u the speed of p immediately after the collision. So there are mainly two ways of finding the answer. Either you can use the conservation of momentum, or you can also use the principle of momentum impulse. So IP or the momentum of IP or the impulse of P is towards the left as seen here, but it should be equals to IQ, but in the opposite direction. So therefore it should also be 4/3 m2u, and using the formula of impulse for P, we have m1 multiplied with the final velocity v1 minus initial velocity, which is u, but as this is to the right, therefore it should be minus u is equals to 4/3 m2u, and so v1 plus u is equals to 4 m2u whole divided by 3 m1. So rearranging for the final velocity v1, we have 4 m2u whole divided by 3m minus u, and simplifying we get 4 m2u minus 3m1u all divided by 3m1. For number C, we have to show that m2 is greater than 3/4 of m1. Now as we know, because the collision is valid, so we can say that this velocity v1 that we found previously should be greater than 0, because otherwise the momentum will not be conserved. And so for number C, we can say that v1 is greater than 0. Therefore Substituting the expression, we have for m2 u minus 3m1 u all divided by 3m1 is greater than 0. So we can multiply both sides with 3m1 and we will get for m2u minus 3m1u is greater than 0. Therefore, for m2u is greater than 3m1u. So we can divide both sides with 4u and we will get m2 is greater than 3m1u divided by 4u. Therefore, we have our required expression or our required inequality of 3 by 4 multiplied with m1. And this is our answer. For our next question, we have May 2020, question number 1. Two particles P and Q with masses m and 2m respectively are moving in the same direction along the same straight line when they collide directly. Immediately before they collide, P is moving with speed 4u and Q is moving with speed u. Immediately after they collide, both particles are moving in the same direction and the speed of Q is 4 times the speed of P. Find the speed of Q immediately after the collision. So for number A, we also have to draw the diagram again. If this is P with M1 and if this is Q with mass M2, we know that initially the speed is 4u and Q was u because they were moving in the same direction as given here. And after collision, this is M1, this is M2. We know that both particles are moving in the same direction and the speed of Q is 4 times that the speed of P. So if the final velocity of P was v, therefore the final velocity of Q must be 4v. Now we can use the principle of conservation of momentum and say P before or the momentum before collision is equals to momentum after collision, and we can write that in this form: P before is equals to P after, and therefore applying the formula, momentum was P is equals to mv, mass into velocity. So we have 4u multiplied with m here, and as we know the mass of P is m, so we can simply write that being m here instead of m1, and Q is 2m, so we can write that being 2m instead of m2. Similarly here we can also write that being 2m. And so we have m multiplied with 4u using this formula plus 2m multiplied with u because they both were moving in the same direction, which is towards the right. So both will be positive, and we have m multiplied with velocity v. As we don't know the velocity v of P, plus 2m multiplied with 4v as discussed previously. Therefore, simplifying, this is 4mu and this is 2mu, so we have 6mu is equals to mv plus 8mv, so this should be 9mv. So we have v is equals to 6mu divided by 9m, and so the answer is 2/3 of u meter per second. For number B, we have to find the magnitude of the impulse exerted by Q on P in the collision. So I is equals to delta P again, as we have known, which is mv minus mu. So we can calculate either of the impulses because it's going to be the same according to the Newton's third law. So we know the final velocity of Q, displaying that being like this. If this was u and the final velocity was 4 multiplied with v, which is 4 into 2/3, we can say that the mass is 2m and the final velocity was 4 into 2/3 of u minus u, because both of them are towards the right, so both will be positive, and we get 2m multiplied with 8/3 u minus u, and so the final answer is 10/3 mu Newton seconds. For number C, state clearly the direction of the impulse. As we know from this diagram, if P moves here and Q was moving here, then as they collide, P will have an impulse. Then P will have an impulse to the left, and similarly Q will also have an impulse of the same magnitude but on the opposite direction. And so we are asked to find out the impulse exerted by Q on P. Therefore, we are referring to this one, and it should be to the left or opposite to the direction or the initial direction of P. And this is our answer. So now let's move on to the next question, which is from Jan 2021. Question number 2. Two particles P and Q have masses 2m and m respectively. The particles are moving towards each other in opposite direction along the same straight line on a smooth horizontal plane. The particles collide directly. Immediately before the collision, the speed of P is 3u and the speed of Q is 2u. The magnitude of the impulse exerted on Q by P is 5 mu. So similarly, we have to draw the particles again. If this is P and if this is Q, this should be 2m and this should be m. And we know that before collision, this should be 3u. And they are moving towards each, therefore Q should be moving opposite with a velocity of 2u as given. And after the collision, we can say that if this is P and this is Q, P receives an impulse of 5 mu to the left and Q receives an impulse to the right of 5 mu according to Newton's third law. Therefore, we can use the theory of impulses by resolving to the right. For IP, we can say that delta P is equals to mv minus mu, or the change in momentum as represented by delta P. So, because we're resolving to the right, this impulse being left will become negative. So we have minus 5 mu is equals to mass, which is 2m multiplied with final velocity v, which is unknown, minus initial velocity, which is 3u, because this is to the right. And so we get minus 5 mu divided by 2m is equals to v minus 3u. Therefore, making v the subject, we have 3u minus 5/2u, as the m cancel each other out. And so we have the speed be 11/2u meter per second. Similarly, for number B, resolving to the right, IQ, or the impulse of Q, is equals to mv minus initial velocity u, which was 2u here. And because if we remember the diagram, 2u was to the left and we are resolving to the right, therefore 2u must be negative. So we have minus 2u. As we know, impulse is 5 mu because we're resolving to the right, and whole divided by n, so we get v plus 2u. Finally, we have v is equals to 5u minus 2u, and the answer is 3u. For the next question, we have a question from 2021 June. Number 1. A particle P has mass 3m and a particle Q has mass 5m. The particles are moving towards each other with opposite directions along the same straight line on a horizontal surface. The particles collide directly. Immediately before the collision, the speed of P is ku, where k is a constant, and the speed of Q is 2u. Immediately after the collision, the speed of P is u and the speed of Q is 3u. The direction of motion of Q is reversed by the collision. Find in terms of m and u the magnitude of the impulse exerted on Q by P in the collision. So for number A, if we draw the situation again, this is P with 3u, velocity of Ku as given. If this is Q with an initial velocity of 2u, mass 5m, after collision, P should have an impulse I here, and Q should have an impulse of the equal magnitude but opposite direction of I. And the velocity of P is u, but we don't know the direction, so it could be either here or could be here. And the motion of Q is reversed, so this should be 3u. So for number A, we can use the formula I is equals to delta P, or change in momentum, mv minus mu. Therefore, we can say I of Q should be, because we know the final velocity which is 3u and the initial velocity which is 2u, and so resolving to the right, we can say that IQ is equals to mass which is 5m multiplied with the final velocity which is 3u to the right, and because initial velocity 2u was to the left, therefore we should have negative 2u, so minus 2u, and so this is 5m 3u plus 2u, and the impulse is 25 mu Newton seconds or kg meter per second. For number B, as I mentioned, there are two possible directions for the velocity or the final velocity of P, which could be towards the left or towards the right. So we can consider two cases, either for P after collision, it can have a final velocity of u towards the left or a final velocity towards the right of u. And as usual, this is the impulse and this is the impulse as shown before here. And we know the impulse is 25 mu. Therefore, for the left side, we have 25 mu is equals to 3m u minus ku, because we're assuming that left side is positive, and as we know, ku was initially moving to the right, therefore ku should be negative, and so this should be 25 mu by 3m is equals to u plus ku. Therefore 25 u by 3 minus u is equals to ku, and so k is equals to 25 by 3 minus 1, dividing both sides with u. Therefore k is equals to 22 by 3, or using the other alternative direction, resolving to the left again, we have impulse which is 25 mu is equals to mass which is 3m again, and final velocity would be minus u because u is towards the right, minus ku because ku was also towards the right as discussed previously. Therefore 25 mu divided by 3m is equals to minus u plus ku. Therefore we have ku is equals to 25 mu by 3m plus u. So k is equals to 25 by 3 plus 1, which is also 28, by 3, and this is our answer, either 22 by 3 or 28 by 3. For our last two questions from October 2021, question number 2. A particle P of mass 2m is moving on a rough horizontal plane when it collides directly with a particle Q of mass 4m which is at rest on the plane. The speed of P immediately before the collision is 3u. The speed of Q immediately after the collision is 2u. Find in terms of u the speed of P immediately after the collision. For number A, let's draw the particles again so that we have a good grasp of the situation. So this is 3u towards the right, this is 4m, and after collision, this is 2m, this is P and Q, and this is also P and Q respectively. This is 4m. We know that the final velocity is 2u, and for Q, it is v, as we don't know, and Q was initially at rest, so u is equals to 0 here. Therefore, we can use the conservation of momentum principle. P before is equals to P after, just like before. Therefore, P before was momentum of P, which is 2m multiplied with 3u. As we know, P or momentum is equals to mv, mass into velocity, plus 4m multiplied with 0, yielding 0 because it is at rest, is equals to 2m multiplied with v, which is the final velocity that we don't know. For q, it is 4m multiplied with 2u. Because all of the speeds are in the same direction, therefore they will all be positive. On the left hand side, we have 6mu, and on the right hand side, we have 2mv plus 8mu. Therefore, we have 6mu minus 8mu is equals to 2mv. Therefore, velocity or the final velocity of P is equals to minus 2mu divided by 2m, and so the velocity is minus u, meaning that velocity v is not in this direction, rather it is to the left. And as we know, the speed does not have any direction, so speed should be u meter per second. For number B, we have to state clearly the direction of motion of P immediately after the collision, as just like before, the motion of P is reversed, so we can say that should be in the opposite direction of P, so we write that should be in the opposite to the direction of P. For number C, is given that following the collision, Q comes to rest after traveling a distance of 6u squared by g along the plane. The coefficient of friction between Q and the plane is mu. Find the value of mu. So if it's the surface, which is rough, so it will have a frictional force. We know that the initial velocity, rather the final velocity of Q was 2u, so this is 2u, and At a point, it comes to rest after traveling a distance of 6u squared by g along the plane, and we know that the coefficient of friction is mu, and this should be the weight, which is mass into gravitational field strength, which is mg. So we should have 4 mg as its weight, and this is the reaction force, and frictional force or F max should be acting towards the left. So first let's resolve vertically or upwards, and we can say that R is equals to 4 mg. So towards the left, the only resultant force is friction, which causes a decelerating force. We can say F max is equals to mu R, which was discussed in our previous video, and so we have 4 mu mg, as mu is unknown, and resolving to the left, F max is equals to mass into acceleration, as this is the only resultant force as mentioned before. So F max should be minus 4 mu mg, just to show that F is acting to the opposite of the particle, so it is resisting, so it should be negative, is equals to mass, which is 4m multiplied with a. So the acceleration is minus mu g. Now we know that the initial velocity was 2u, u is 2u, displacement is 6u squared by g, final velocity was v is equals to 0 because it comes at rest, and therefore we know that acceleration is minus mu g. So we can use the equation v squared equals to u squared plus 2as, and substituting the values, final velocity is 0 squared, which is 0, initial velocity is 2u whole squared plus 2 into acceleration, which is minus mu g, plus s, which is 6u squared by g as mentioned here. Further simplifying, we can get 0 on the left side, 4u squared on the right side, minus 2 multiplied with 6, which is 12, and mu remains same, g gets cancelled out, so we have minus 12 u squared mu. And so moving this to the left, we have 12 u squared mu is equals to 4u squared. Therefore mu or mu is equals to 4u squared divided by 12u squared, and the answer is 1/3, or to 3SF or 2SF, we can write that being 0.33, and this has no units. For Jan 2022, question number 2, which is the last question. A particle P has mass km and a particle Q has mass m. The particles are moving towards each other in opposite directions along the same straight line when they collide directly. Immediately before the collision, P has speed 3u and Q has speed u. As a result of the collision, the direction of motion of each particle is reversed and speed of each particle is halved. So for number A, we first have to draw the situation again. If this is P and this is Q, this is after the collision. P has a mass of km, Q with m. Similar, this is km and this is m again. So we know that initially P had a speed of 3u, m had a speed of u, but in the opposite direction as they are moving towards. Finally, we know that the speeds are halved and the direction of motion of each particle is reversed. So this should be 3 by 2 u because it is halved, and this should be to the right of u by 2. And we can resolve towards the right and use the conservation of momentum. P before is equals to P after. P before was Km multiplied with 3u plus m multiplied with minus u, because u is towards the left and we are considering that the right side is positive, equals to P after, which is Km multiplied with minus 3 by 2u, just like previously this is towards the left, so negative, plus m multiplied with u by 2 because this is towards the right, so we have 3mk u, so we have 3kmu minus mu is equals to minus 3 by 2 kmu plus mu by 2. We can multiply both sides with 2 to get rid of the fractions and get 6 kmu minus 2 mu is equals to minus 3 kmu plus mu. Making k the subject, we have 6 kmu plus 3 kmu is equals to 2 mu plus mu. 6 plus 3 is 9, so 9 kmu is equals to 2 plus 1, which is 3 mu. Therefore k is equals to 3 mu divided by 9 mu, so the value of k is 1/3. For number B, we have to find the magnitude of the impulse exerted on Q on the collision. So referring to the diagram again, if this particle is Q, impulse will be received here. Using the impulse formula, I is equals to change in momentum, which is delta P. We have IQ towards the right of being final velocity is towards the right, so this is mass of m u by 2 minus, because the initial velocity was u to the left, so it should be minus u, and so the final answer is m multiplied by u by 2 plus u, and the final answer is 3 by 2 mu Newton seconds. So this brings us to the end of our video. Thanks for watching it. Please make sure to leave a like, comment, share and subscribe, and see you guys in the next video. Goodbye.